Alright, now we have discussed with no RAM. Let's try the helper of the RAM. It's kind of how can we use the RAM to make our algorithm faster. So just by looking, we have defined that hey, we C is the winner by being the least character that's visible in this list of characters. Alright, so we will use hash map or hash table or dictionary based on whatever language you're used to write. They are all the same, but based on the programming language, they have different conventional name. Anyway, we will keep track of the repeated characters by storing the character as keys in the hash map. Like this one, we have A, B, and C and D. Those are the unique characters that's in our list, and 5 is the repeated count, 2 is the repeat count, 1, 2 also are the repeat counts. Alright, so now let's check the solution. We have the least repeat characters size, which is in our case, considering the worst case is they are all repeat, so the size plus 1, which is gonna be 11. So we need to make sure that any character would uh, would overtake this least repeat character. Anyway, that's just for coding for the coding solution. If you don't really care about it, just ignore it. Anyway, moving on, we have our current iteration. Now let's see how can RAM effectively improve our code. So we'll start our iteration by this position, and we're gonna iterate one time and only one time throughout this list, and we're gonna always update the characters that's visible in our current iteration. So first we have at the point position A, we'll start by 0 and increment it by 1 to become 1. We'll increment it another 1, increment 1 again, and now we're at 3. Let's get to another character. It's gonna be at size 1, 0 plus 1, because 0 does that mean it doesn't really exist, and plus 1 we're just incrementing it. B, the same, incremented by 1. D, starting 1 and incremented by 1. Now we're investing back 1, we just incremented by another 1. B, incremented also by 1, and finally A. And after the single iteration throughout this list, now we need to iterate to the hash map and find the least repeated character in that hash map. And we need to ask ourselves, is it lower than the current list? And the current list in our case would be 11 based on the size of this list plus 1. So we are 100% sure that we're gonna find a valid value here. So in our case 5 is smaller than 11, so we're gonna take it. We have this 11, 5 is smaller than, so we're gonna take 5. We're gonna iterate by B. B is 2, B is smaller than the previously 5, so we're gonna take 2. Now we're visiting C, which is 1. 1 is smaller than this 2, which we already stored it, so we're gonna take 1. We're gonna visit the last key, which we have D. D is 2 is greater than C, so we're just skipping this approach. That's the amount of iterations that we're gonna need to implement to find this find the least repeated character. So now we have the result of 1, which is representing we have the result of C, which represents just single count, one count of the repeated character. Alright, so now we need to understand some kind of basic understanding of big O notation in terms of execution times and RAM or space complexity. So for execution steps, this took 10 steps for first iteration throughout the list, then another 4 steps for the hash map. Those are the steps which we have taken. In our best case scenario, we must iterate through the list and it will only contain one character, ultimately iterating through the list plus one hash map, because the one is the size of the unique value in that list. So basically will be one key in the hash map so it's gonna be of n plus 1 gonna be of n, where n and 1 are just same, so you can consider it as 2n. But basically if it's just single one and we know for a fact it's gonna be 1, so it's gonna be n plus 1, so of n. Anyway, that's for best possible case. Now for the worst possible case, we will need to have steps as the size of the list, where every element in the list will be a unique key in our map. And this way is gonna be, we're gonna call the size of the list n steps. We'll call it n, not steps, it's just n, and it's gonna take steps of n because we're gonna iterate through the list, and we were gonna have a hash map. This hash map storing the unique keys, which is already every step, because every step in our list is gonna be a unique character. Considering every element list as unique character, calling it m steps, which is the same as size n, so ultimately it's gonna be O of n plus n equals to n. That's the worst case in terms of execution steps. So basically now we have, in terms of big annotation, we're taking the worst case of whatever is the highest possible number of steps. In our case, it's gonna be n plus n, shortening it to of 2n. So overall, big annotation, or what you can call it time complexity for this algorithm, for that execution, is gonna be O of 2n. That's for execution steps, that's for time complexity. We have not talked about RAM yet. Let's visit the RAM and discuss what happened. Let's remember, RAM or time complexity, space complexity. Space complexity is calculated for the extra spaces. So now, what extra spaces we have taken in order to solve this algorithm? We have taken the hash map. We have used this hash map to solve our problem. The list we have got is given to us. We don't calculate it as extra space. We couldn't really use it as extra space because that's what's given to us. We're using extra hash map here. So the extra RAM usage, which is the extra hash map data structure. Right, so the highest size for this hash map, which is the worst case scenario, is going to be the same size of n. Therefore, the extra RAM space complexity would be O of n. So the overall space complexity or big O notation for that extra RAM would be O of n. That's for RAM, that's for the extra RAM, that's for the space complexity. So let's recap what we have done for this algorithm. For the time complexity, we have taken O of 2 of n, and for the space complexity, we have taken O of n, where n here is the size of the list that we're given, which is the list of characters which we are given. So that's basically how we can use RAM effectively to save up steps. Remember, in the previous algorithm we have taken n square, but now let's say we have n of 9 here. So 2 times 9 is 18, but if we have taken the previous algorithm, would be n square, n times n is 81. So we have saved almost like 70 or 80 steps, just saving kind of 70, 60, 65, this kind of range, but we have saved this number of steps. But in trade-off, we have used space complexity. We have taken more RAM, we have taken more space complexity, we have taken extra space in the RAM. That's basically how can we use RAM to make the algorithm more effective. And every time you scale up, you need kind of understand how this number decreased dramatically. So that's basically how can RAM work with an algorithm, and this was an example to show how can we benefit from the RAM.